Hello and welcome back to the channel. I am Sachleen and we are back with a new video. And this time we're going to talk about why does complexity actually matter. So you might have seen a programmer sitting cluelessly in front of his monitor and talking, I need to reduce the complexity of this program. Now what does he actually mean? Before that, let's just see what kind of complexities do we have to deal with. So we've got two kinds of complexities. One is space complexity and the other is time complexity. Now, in easy terms, space complexity is the amount of memory or RAM your computer uses to execute your program. And time complexity is the time used by your computer to solve the problem or to find a solution. Well, complexity may vary according to the number of iterations. So it may vary according to the number of iterations your program actually goes through. We can actually further divide the number of iterations or the complexity into three cases, which is best case scenario, average case scenario, or worst case scenario. Let's see what kinds of these scenarios are. Suppose you've got something graph like this. Let's number them quite very quickly. We've got a graph with 3 levels. You can call this a tree with 3 levels. Right? Level 1, level 2 and level 3. Now the rules are that you need to traverse from left to right, and only when all the nodes on a certain level are finished, only then you can move towards the next level. If I ask you to find one, it will be a best case scenario. Let's just color code this. If I ask you to find something between 2 to 6, just for the case of the argument around 5, it will be an average case scenario. And if I ask you to find something around 7, this will be a worst case scenario, because for 1 you will actually have to traverse nothing but just the first node, whereas for 5 you will be traversing 2, 3, 4 and then 5, but for 7 you will be traversing all of these as well as 6 and 7, and this totally comes at the last of your search. So this is a worst case scenario. So there will be 3 kinds of cases which you can actually find out depending on your iteration. So today we'll be actually looking at how to reduce the complexity, basically using an example of prime numbers. Just see what prime numbers are. Prime numbers, by mathematical definition, are a number is actually a number which is divisible only by 1 and self. That is all. That is what the mathematical definition for us is. But as you know, computers cannot just go on dividing all about every number. What we need to do is we need to define a certain kind of algorithm which will allow us to find out that if a certain number is prime or not. So what we can do is we can use the number as always as n. Then we can use the modulus operator, which provides us with the remainder of a certain number, dividing it by another number, which will produce some remainder. So this will be our remainder. Now this is a remainder, like this is actually the modulus operator, and which will provide us with remainder. Now yeah, so thing is, this is known as the modulus operator, and this is where you'll be finding the remainder. Now what we need to do is we need to see that if it actually provides us with something as 0. We need to stop immediately, and we can safely say that the number n is not prime. I think things have got complex right here. So what I can do is we can explain this by a very short example. So if 6 modulus 2 gives 0, which obviously it will, because if you divide 6 by 2, it completely divides 6 by 3, provides us with 0. So if we get 0, we need to stop right there. Then we can say that yes, 6 isn't a prime number. The question is what this number will be, and this number will be actually the deciding factor in our complexity. Let's move on to our coding part. Okay, so the IDE which we are using is Jupyter, and the programming language which we are using is Python. We've already imported two libraries, which is time and maths. Let's get coding speed. N equals to int. Let's just input something very quickly, and we can ask the user to enter a number for us, please, and write it. Then we use a variable to store current system time. Then this will actually start our stopwatch. Then use for I in range to n. This translates in Java to for I. Let's just quickly write. If I would have written this in Java, this would have been for in I equals to 2, I less than n, I plus plus. This is exactly the same thing which I would have written if I was coding in Java. So if n modulo of I equals to 0, shout for me that the number isn't prime and break at that instant, right? So let's just test this out just for the sake of it, and if I just press 6 for myself, and you can see that the number isn't prime. So yes, this is working quite nice. And if you actually, this is what I'll be saying to the program, that if you actually carry out all the iterations, then you need to print the number is prime, and also print the execution time, which will be the system time at the end of the execution minus the start. Right, so let's just see, and if I press 5, I get the current system, like I get the execution time, which is 0.0015 seconds, which is quite nice and appreciating this. Now let's just use our test case, which is 97, and we see that we actually get around 0.0005, and if we just run this again, we get around 0.0015, which is quite regular. So we can actually say that we get, for 97 we get around 0.0001. So let's just place this here. For 97 we get 0.01, right? 0.001, right? So for 97 we get 0.01 seconds, which is quite nice. Now let's just test this for another one, which is this number right here. Let's just copy this out, place it here, ask the program to run this for us, and we get around 0.12. Let's just run it for another iteration, and we get 0.2, and let's just run it for another one, we get 0.11, and for another iteration we get 0.15. So I think 0.15 is doable, because we were getting values from 0.10 to 0.2, which is 0.15. And now let's just go on for our biggest value, which is this, and now let's just run this, and now we see that the program is taking quite a significant amount of time to run this program. It is still carrying it out, so I think it will take around 9 seconds, which was what I was getting around first, but now it has taken around 13 seconds. Well, we'll just place this because we can't actually afford to waste time. Now how can we actually reduce this? If you look deeper, if you see or you find out the factors of a number such as 6, you can see the factors actually gather around. So if you take 6, you get 1, 2, 3 and 6 itself. So you see that factors actually carry around half of it. So if you see this more clearly, of a number around 28, you can see that maximum factor you can find is around 14. So carrying this out, we'll just copy this, paste this, and now we'll just reduce the iterations from n to n by 2. Now let's just test this for 97. We see that it comes around same, and now let's just test this for the number 5247, and we can now see that now it has reduced quite a significant amount of it. So it has reduced around 0.8 seconds. Let's just do this again just for the sake of this and see again. It is reduced around 0.8 seconds. So that is a huge difference. Now if we go on to check for the biggest number which we have, and you see that it will still take around 4 to 5 seconds based on the CPU usage. Now it took around 6 seconds, which is still fine because it took a whopping 7 seconds less than what the previous iteration of this took. If we actually ponder upon this more, which is a bit more mathematical aspect, we can also notice that if I have to get something, like let's just take the example of 28. Well, if I have to take the factors of 28, well, let's just go back to our drawing area, and now I have to take the factors of 28. So you can see that I have got 1, 28, 2, 14, 4 and 7. What I can see here is they have a certain correlation between them, which is 1 corresponds to 28, 2 corresponds to 14 and 4 corresponds to 7. The thing is that if it is going to be flagged at 14 or even 7, it will be flagged at 4 and 2. What this tells me is that rather than going even till half of it, what I can go is till the square root of the number. If I go at the square root of the number, which will be, let's just say that I want to find out something of a number which is 16, and let's see that if this is prime or not. We get 1, 16, 2, 8 and then 4. The thing is that 4 is being multiplied by itself. So the thing is that if 4 is going to be flagging 16, the other 4 is also going to be flagging 16. So exactly at the square root line, we can say that this will be the deciding factor, right? So let's now copy this again. We've already copied it. So what we can do is we just need to typecast this square root function, which is sqrt, from the math library and use this. So we've got all the three of our cases right here. Let's just copy this and run this. For 97, we do get the number quite a bit low, which is like around 0.005 seconds, 0005 seconds, which is even less, which is almost the half of our previous one. So it comes around 0.0005 seconds, which is quite incredible. Let's look at the second or the average case. As you see, we've again been able to get around 600th of a second over this. And if we look at the greatest number which we've got as a test case, or you can say as our worst case scenario, under a second, this is totally incredible. We'll just run this again just for making it sure that this was no fluke, and you can actually see that yes, it is around 0.003 seconds. Now this is the same number which the first program took around 13 seconds to execute, and the latest program is actually taking less than a second. Now if we actually go back and run this again, this still might take more than 9 seconds, which is huge. Now this is the difference between a very complex program and a program which has a reduced number of complexities. So as you can see, the program has not yet executed as it is showing a star and it took 15 seconds. So 13 seconds was a much better number. And if we actually execute this again, we still get this we get this back in less than a second. So complexity plays quite a big role in programs, and this was just to show that yes, there is always somewhere which you can improve on. Thank you and keep practicing.